Swayam Prabha. Digital India. Educated India.
In the last week, we were discussing about the lump system analysis. We discussed different elements such as inertance, compliance, and how do we arrive at the simplified expressions, where lumped analysis really mean that all the continua, 1D or 3D continua, they are approximated as one, the entire continuum is approximated as one particle which is behaving in a certain manner. So, we consider the case of a constriction sandwiched between two large volumes, and then the case of a short cavity which is closed at one end. So, we derive certain expressions like I was mentioning, and in this week we are going to proceed further in that direction, and for that end we will revisit the case of a cavity which is closed at one end, and we have a sort of piston excitation at other end, and the length is L. So, we saw that the impedance of such a system was given by rho naught c square j omega by V c, or it could be written as gamma times P naught by j omega V c. V c is the volume of this system and P naught is your atmospheric pressure. Now, how did we arrive at this expression? We saw that tan K naught L is approximately equal to K naught L. With this approximation we derive this expression, but remember, if you recall, tan K naught L, if it also has this term plus K naught L cube by 3 plus this thing. So, how about if we retain this term and neglect the higher order terms? So, higher order terms are neglected and we retain the underlying terms in the expression and see the magic, what happens. Well, in such a case, what happens is, the reason why I am doing this, and it will be soon be evident why this is important. So, Z input impedance then given by Z naught divided by J K naught L and 1 plus K naught square L square by, this is capital L, I am sorry, by 3. So, what is your Z naught? Z naught is the impedance seen. So, basically once we simplify this thing further, this particular expression, we will see that this is nothing but Z naught divided by j K naught L, and we apply the binomial theorem to simplify the algebra minus 1. So, this is approximately, neglecting this will be infinite series, binomial series. We neglect the higher order terms, again under the same approximation K naught L is much less than 1, but the difference is that we consider the additional term. So, what we are going to see is basically j K naught L 1 minus K naught square L square by 3. So, when you simplify this thing further, we are going to get j K naught L plus j times K naught L by 3 times Z naught. So, this is what we are going to get, and Z naught of course is your rho naught C naught, the characteristic impedance. So, what does it mean? What does this expression say? Let us number this as 1. What does this mean? So, it means that the net or the actual impedance that is seen is nothing but rho naught C naught square times j omega V c plus j omega times rho naught V times 3 S square. Then this term, the second term, is then a correction to the first term. So, this term is well acquainted with, we saw that in the last lecture, and this clearly is a compliance. This is more like a 1 by j omega c, and this is j omega L. where L here can be thought of as V rho naught by V 3 S square. So, this is, you remember j omega L. So, L has this form rho naught times V c, I would say this is V c by 3 S square. S is a cross sectional area. So, it will satisfy the dimensionality things, and what basically it means is that the correction term, which is the underlying term here, this is a positive reactance that is associated 1/3 mass of the fluid in the cavity. So, this is not quite a very unexpected result. This is not very surprising, because the moment it is like a spring, and if you have a bob or a mass on a spring and the mass of the bob is say m, and the spring also has certain mass ms. So, we typically from our elementary courses in vibration, we see that the net effective mass is given by root the net frequency then is given by root over k by m plus ms by 3 or something like that. So, this is just for discussion that this factor of 1 by 3 that is coming here that is exactly like a additional mass that is seen by the cavity. The impedance seen by the piston here is if you consider the additional term, it is like the additional mass of the air that is also accounted for, and that shows as the inertance. That is a first order correction to the low frequency approximation. But physically what it also means is that the short end cavity, if it is not all that short, you have two things that are acting in parallel. So, this has a form of j omega L, this is j omega c. So, this inertance term is present when you consider a correction term. So, this inertance acts like a correction to the compliance, which is like a more fundamental behavior of such a short end cavity, and in a way both your compliance and inertance are sort of active or operative, and they act in series. So, the circuit electrical circuit, electroacoustic circuit of short end cavity, when you consider such a correction, is then given by inertance and your compliance, which both act in series. So, if you consider the points here something like this, it is like inertance L and your compliance C, they both act in series, and this of course is a correction to this term. And if we recall our discussion for the Helmholtz resonator, which was something like a big some irregular cavity and this kind of a thing, exactly the same thing is going on. You have your basic behavior is that of inertance j omega L, and for this thing is 1 by j omega c. So, both of them add up. So, net impedance, like what we discussed in the last class, let me go to the slide. The last class we saw this was a system j omega L by S and plus gamma times P naught by j omega V c. So, when we simplify the matter, simplify this thing and find out the frequency at which the impedance goes to 0, this is also imaginary, this part is imaginary, this part is imaginary. So, when we simplify the algebra and find out the frequency where the imaginary part of the impedance is going to 0, so we will get the resonance frequency for the lumped system analysis. But before we go about doing that business of finding out the resonance frequencies of a Helmholtz resonator, it is probably prudent to first talk about the end corrections for the first time. So, let us introduce the concept of end corrections. So, what do you mean by end correction? Let us consider in the first lecture of this week we discussed very briefly, although very briefly, this is a research matter in itself. If we have an open ended tube with a flange, with an infinite flange going to infinity here and going to infinity here, and you have waves that sees the impedance at this cross section area what I just drew. So, what is going to be the effect? What is going to be the impedance that is seen? So, basically the idea is to get some sort of a realistic expression for the impedance. One can actually argue that there is fluid in the duct and we can simply put the condition P tilde 0. So, it is an open ended condition. While this is not all that inaccurate, the fact is that when a wave is incident say from this part, an open ended condition would mean the entire wave is reflected back in the opposite direction. So, if you have wave going like this in its entire, and the wave is completely reflected back. However, this is usually not the case, because suppose you have a wave coming in from here and you have a certain wave that is reflected back, some amount of acoustic power also propagates downstream into the open end, and that is what causes all the drama, all the mathematical things start to fall then, because this is really the some amount of partial transmission is going on, and so it is necessary to account for the impedance seen here at impedance imposed by the atmosphere. All this atmosphere, whatever impedance it imposes on the wave that is incident at this point, we are going to account for that. And what it physically would mean, we will see by some simple algebra, that it means there is an extra column of air, just hypothetical column of air sitting here, and it is like an addition of an extra mass. So, it is like an inertance term that is added. So, before we do that, let me just write down the expression for the impedance Z naught that was seen, that we derived a few lectures back, R plus J x naught, impedance for a open tube with infinite flange on both sides. So, in such a half space, it is also called half space mathematically. So, R naught and x naught take certain forms. So, the entire expression would basically look like rho naught C naught times S. S is the cross sectional area of the pipe, and this would become R into 2 of K naught A. A is the radius, for example, and J times x1 of this thing. So, what is R1 then? R1 of 2 times K naught A is the expression given by 1 minus 2 times Bessel function of 2 times K naught A divided by 2 times K naught A. So, when you simplify this thing, we are going to get, if you recall our last, probably the first lecture of this week, square of this times 2 times 4 minus 2 times K naught A to the power 4 divided by 2 into 4 square into 6 square and plus your higher order terms. So, we can very safely approximate this by retaining only the underlying term. When we do that, what are we going to get? We are going to get K naught A whole square by 2, this approximation. And similarly, what about the term that is present here, x naught? So, this, let me spend a little time here. So, what is R naught term? It is like a real part of the impedance, and that is basically a lossy, that represents loss, and this is the reactance term. It is also called the resistive term, or the real part of the impedance, and it denotes loss in the fluid, or not in the fluid due to the radiation, and x naught is the reactance term. That, so if you integrate the power, there will be a certain power that will be lost. So, if you do something like u square times z dt and integrate it over a certain time, and you actually put this thing z naught here, the entire quantity will be non-zero because of non-zero behavior of this. That means certain amount of energy or acoustic power is lost per cycle, because R naught is non-zero. So, the reactance does not contribute to the power loss. It is just like energy being, acoustic power being shifted in the acoustic potential energy or acoustic kinetic energy of the particles, but it is R naught that contributes to the loss. And x naught, the reactance, the expression for that can be written down like 4 by pi into K naught A, and this is 2 for dimensionality, and this is 3, and there will be higher order terms, K naught cube divided by 3 square times 5 plus higher order terms. So, we will have to make certain approximations here. Again 2 times k naught a by 3 pi is what we are going to get. So, how much is your 8 by 3 pi? So, that is approximately equal to 0.85 and times k naught a. So, this is what we are going to get for this part, and we obviously have the expression for this thing. So, the net impedance that is seen at this point by a wave is can be written safely in the low frequency, that is k naught times a is much less than 1. So, if you have a pipe whose radius is a, and for low frequencies when you have k naught a is much less than 1, Z actual impedance can be written as rho naught times C naught times k square by 2 pi. So, we are trying to simplify things, and plus j omega times rho naught s by s square into 8 a by 3 pi. So, this of course follows from certain simplification. You have your 8 a and 3 pi I have clubbed together, k naught I have taken and actually I have put omega by C naught, and some simplifications were done to finally arrive at the actual impedance seen by the wave here. So, the idea is that this is the expression. So, the right hand side then is dominated by the positive reactance, that is your this part, underlying part, and it has a mass which is equal to rho naught times s into 8 a by 3 pi. So, what pi? What does it mean? It means that this is obviously kg by meter cube, this is meter square, and this is the length, meter square. So, the idea is that at this point we have an additional mass or a small, the moment this wave arrives at this point, at the interface of the atmosphere and the end of the tube, it does not see a zero load. Zero load means we have this condition p tilde 0, which is not the case when you do this thing. We have a finite load, and the load consists of mainly a short continuation of the tube. It is like the tube is not really ending at this point, it is slightly extruded. So, if you have a certain tube here and you have an infinite flange here, the tube does not just end here, there is small amount of a tube that is protruding out, hypothetical tube. So, there is a length. What is the length of such a small tube of the same radius? Radius is the same, S is the cross section area. So, the length is 8 by 3 pi, that is basically 0.85 times A. So, if A is very small, like typically say 40 mm for automotive mufflers, so we can easily work out the small protruding length, hypothetical length the wave would see. So, this is like your end correction, and we will see why this is important as far as resonance frequencies are concerned. Similarly, now if you have, suppose typically you have things like big sheets, or let me draw things for you, or you have things like this. So, you have holes that are distributed across the face. So, you can call this as plates with perforated hole. So, typically you can bend this sheet. I will show some photographs in due course, maybe you will have some dedicated lecture which shows you nice photograph, you can relate that. This is just a rough sketch of this thing. So, if you bend the sheet across, and you have small holes also called perforates. So, if you have a pipe filled with all the holes, and if you have a pipe like this with small holes everywhere, so this is like, you are trying to bend the sheet into a pipe, and there is a fluid flow here, or air is flowing through the airway, and outside there is an annular cavity. So, on this side you can consider this as a hole with an infinite flange on both sides, and similarly for the hole inside. So, basically when you evaluate the thickness of this thickness T, so it is not just T, it is something like 0.85 times A multiplied by 2, because you see the end correction that is adding here as well as here, meaning that it is the end correction is adding at this side and also this side. So, the net effective thickness becomes 1.7 times the radius A. It is important in a Helmholtz resonator context, we will soon see why this is important. So, this is the net effective length, you can call this TEFF, T effective length, and for small tubes it may so happen that this term, the correction term, actually dominates the physical thickness of the tube or a sheet of metal. So, this term is important, end correction term, and that is because the fluid is seeing a virtual or a hypothetical kind of a thing in here. So, this thing adds on both sides. I hope I am clear, but we will probably can have a question answer session in which you can answer these questions in a more upfront manner. There are obviously situations in which we do not have a case like this, rather we might have a case where you have your tube which is just plainly exposed to the atmosphere. So, when a wave is coming here, some part is being reflected back, but other part is also going. This is much more complicated because the point I am trying to make is that this thing does not exist. This infinite flange business is no longer there. This really simplified the matter, but the fact that it is not there poses considerable difficulty in the mathematical analysis. So, just to keep it simple, I would just say this has been again subject matter of the past research. Quite a few papers are there for acoustic radiation impedance seen at the end of a unflanged open pipe. It is now we have this space also and this space also. It is no longer a half space. Half space means you have only infinite space in one direction, other is constrained. You have almost a full spherical space minus this duct of course. So, the impedance, like I said, was much more complicated to derive. There has been papers, but the important result that we will be using in this course, you might well use, is that typically when you have things like this, the end correction length of the hypothetical fluid cylinder that is added right at the point P, say at the end of the tube, is the length of such a thing is given by delta L is equal to 0.6133 A is the radius. So, you can have situations in which one end is open and the other end is flanged. So, then the end correction will be this one plus 0.85 times A, whatever it is. So, we can consider the corresponding cases as well. So, it depends on the application of the end correction, then is we must carefully choose that. I will present to you one example before I close this particular discussion. Just like we have a Helmholtz resonator, things like we saw things like this being analyzed. So, here also it can be considered flange and this part also is flanged. So, the length is 1.7 times the radius of this part, but you also have a very important muffler element called extended inlet and outlet element. So, you typically have this kind of a structure. So, our analysis would say that this is, say, if the length is L, the length of the tube is L and this is L by 2. So, the impedance or the resonance frequency of this quarter wave resonator would actually effectively cancel out the trough or the first axial resonance of this chamber. We will do all the maths later, but the point I am trying to make here is that you see, carefully analyze this small pipe, and you have a big chamber, something like you have a pipe which is being extended into a big cavity, muffler cavity. So, this can be considered as a case, this case. These two cases in a way are equivalent, because you have a open ended pipe discharging into a almost unflanged domain or a space. So, the end correction, so what we see essentially, say the radius is r naught. So, the net effective length, let us say the length of this thing can be L1 or the extension, net extension. So, the acoustically you will see LEFF is L1 times 0.6133 times r naught. Actually, it will not be that simple, because you also have some bounded, it is after all a bounded media. So, the net effective length would basically become L effective is equal to L1 plus 0.61, let us keep it simple, 0.61 times, instead of r naught there is some additional factor that probably could be considered, and that is 1 minus R naught times big R naught, where this is the radius of the chamber and small r naught is that of the duct. So, when R naught is equal to R, then of course, there is no meaning to this term, but when basically R naught is very small, actually there should be additional things, maybe perhaps it could be R naught somewhere sitting out here. So, then when R naught is very small, then this term can be neglected. Basically the idea is that the inside term kind of acts like a correction term to the classical end correction approach. We will probably worry about these things a little later as we go into the transfer matrix approach and matching conditions and all that kind of a thing. For now, we will probably end this lecture, and in the next lecture we are going to talk about the resonance frequencies of Helmholtz resonator to start off with, and then probably your concentric hole cavity resonators and a few important constituent elements, and then we will worry about probably about the electroacoustic circuits and Thevenin's theorem, Norton's theorem, and those kind of things. That will be probably be taken up in the next lecture. So, thanks a lot, and thanks for attending. I will see you in the next lecture.